Okay, we have here an integral on the board. We've got the integral from 0 to infinity, x to the s minus 1, e minus, I've got the minus sign next to the n, dx. And we have two conditions for our s and n over here that we want both s and n to be greater than 0 for this. This is kind of a continuation. I think I've done now 3 or 4 videos on generalizations of the Gaussian integral. So this is kind of an extension of that because you'll just notice if we have s equal to 1 and n equal to 2, well then this becomes x to the 0, and what we're left with is just the integral from 0 to infinity e minus x squared dx. And for this particular case, this is going to have a value of just square root of pi over 2. So now to get to a general formula for this, we're going to do something pretty similar. I think the same kind of idea as the previous videos on this, where I'm going to want to do a u substitution to clean this up. So we'll do u equal to x to the n. Solve for x, then we have x equals u to the 1 over n. And then I'll take the derivative, dx, just power roll. This is going to be 1 over n u, 1 over n minus 1 du. So I'll go ahead and substitute first infinity to the n, that's going to be infinity. Then when you plug 0 in, that's still 0. Now for the x part, okay, we have a value for x, so we're going to have the exponents are just going to be a little bit messy, so we'll just plug that in for x, and we still have this to the s minus 1. Then this becomes e minus u dx. 1 over n is going to be a constant, so let's bring that all the way out front and then bring in the rest of this stuff. So we'll have u 1 over n minus 1 du. But now we've got the same base here, so let's multiply those together and combine exponents. And let me write it a little bit. Let's see what's going to happen on this just to kind of get some clarity. So like when you distribute this n, this is going to be s minus 1 over n. Then we add the exponents adding this one. Let's create a common denominator. For this 1, I can write it as n over n. So this exponent I can write as 1 minus n over n. But then when you add those together, the 1's are going to cancel and you're left with s minus n over n. But then I'm going to break it up again, divide the n back in, and we can write it as s over n minus 1. So let me just do the rewrite using this now as our exponent on u. And then what we notice here is this is perfectly set up to use the gamma function. You may wonder, why not use a Laplace transform? Well, you can really go either way. In any case like this, you can always go back and forth. My preference is, like, if I already have a 1 on the coefficient here, I like to use the gamma function. If I have something else, I probably use Laplace transform. But it's really just personal preference, and it doesn't matter much. It's just a simple substitution either way. So for the gamma function, using the formula, this is going to be our input right here, just the s over n, as we already have the minus 1 on it. So this whole thing right here is just going to be gamma of s over n. So putting it together, multiplying it out for my final solution of this, we just have gamma s over n, and that's it. And so I think it's a pretty nice formula. We can go back actually to the original and see, maybe as a check, just see that we can get back to the Gaussian integral. So when s is 1 and n is 2, we're going to have gamma of 1/2, and then the n's 2. Well, gamma of 1/2 has a well-known value of just square root of pi. So we get back our square root of pi over 2 for our Gaussian integral, or half the Gaussian integral from 0 to infinity. And of course, you could play around with different values, just looking out for this restriction. I think other values would work, but you just have to keep in mind that the gamma function is not defined for 0. It's not defined for negative integers. So of course, n can't be 0. So there's definitely restrictions on it. But so you have some restrictions, but you can get a lot of nice values with this formula. Okay, so that's it for today. Thanks everyone for watching. Have a good day.